In the last video, we talked about Fubini's theorem and we did an example over a nice box. Great, but what do we do if our domain isn't a box? Well, we've encountered this problem before, and what we ended up doing was we looked at what we called elementary regions. There were type 1 and type 2 elementary regions. So maybe a good time just to review that. Again, that was in 5.4. The first time we came through this section. Now we're just coming back to it with looking at higher dimensions. And so then, if you remember, we might think of our space W. We could say, okay, well, W is a set of all X, Y, Z. And then we're not going to call type 1, type 2 regions here or anything, just because it could be really annoying to think of all the different permutations here. But we would think of perhaps our region W as, okay, X is bounded between two nice constants, and then we might need to write Y as bounded between two functions of X. Let's call it gamma of X and delta of X, okay? And then Z is going to be bounded between two functions of X and Y, so perhaps phi of XY and psi of XY. And so this is, again, one type of elementary region. There's a lot. I think, in fact, there's 6 different types, so we could do type 1 through 6, but let's not do it. There we go. And so then, once we're able to represent the functions, or the bounds in terms of the other variables, then we're good. We're good to go. Okay? And then in terms of Riemann sums, again, just keeping in mind that, okay, we went through that process in the first video of how we actually do triple integrals, and then in there, if we want to think about indicating whether or not we are in the region of interest, remember, we might have to expand our region to make it into a box. That's where that extension function idea comes into play. Okay, so we could make it into a giant box, so enclose the region that we're talking about, or that we're integrating over in a box, and then use f extension as a way to indicate whether we're actually in that function that we are interested in or not. Okay, so here's an example. Alright, so we have a continuous function with domain given by, okay, and in the first octant. Draw the region and set up the following integrals. Okay, well, it seems simple enough. So if we draw the region, we have our... okay, so drawing in 3D is fun, yes, and you know I'm an awesome artist, so as are all of you. So here are the points. I'm going to call those all values at 1, and here's kind of the boundary that we would see. Okay, and at least in the first octant, and then we go ahead and shade. Okay, so here's our domain of integration. Okay, and it would be actually the tetrahedron, so it would be, we'd actually have the axis lines here. You can't really see the axis lines on my drawing, but it would be the tetrahedron there that is below that plane. Okay, so then that's great and fine and well. So let's start backwards in our integration. Okay, well, alright, so if we're doing X as the last one, so this is an elementary region. It's certainly not a box, but it's fine. We can try and set this up using elementary region. So X is going to go from 0 to 1. Okay, because we have to do that. And then now if we think about Y, we want to formulate Y as a function of X. Well, if we look in the XY plane, right, Y should extend from 0 up to that line there, so that's going to be 1 minus X. Okay, and then when we think about Z should extend, so now we're out to there, but then I need to send Z eventually up to 1, but it actually needs to border on the plane, right? So Z should extend from 0 up to 1 minus X minus Y. Okay, and then now in part B, all we're doing is changing the order. So if we want x to be last, that really hasn't changed. But then now I have to look in the xz plane. So if I'm doing that, let's put this in purple just for change, 0 to 1. Okay, so xz plane, x is going from, or sorry, in that plane, z is going from 0 up to 1 minus x. So there we go, that's our bounds for that one. And then the last one in y, similar thing, now I just need to go out. So 1 minus x minus z should be the boundary there. All right. So again, nothing, we've seen this before, but now it's been a while, so we're just kind of reviewing it. All right. All right. Final departing question. How can we use a volume of a region R to find, or sorry, how can we find the volume of a region using triple integrals? Well, remember how we found a surface area using a double integral? Well, very, very similar. We're just going to take triple integral over our region R of 1 dV. Our function is just 1. Okay, and that'll give us the volume for a region R. Okay. Might be handy in homework, group work, etc. All right, so that's the end of this video. In the next video, we'll look at more change of variables.